telescope pointed at nothing, a tiny black patch of sky, no bigger than a grain of sand held at arm's length, and found thousands of galaxies. That's the James Webb Space Telescope. And inside those images, scattered like blood drops on black velvet, were tiny red dots that should not exist. Galaxies as massive as our entire Milky Way, packed into the universe's first few 100 million years, when physics says there wasn't nearly enough time to build them. Scientists called them little red dots. They argued. They panicked. And now, finally, the answer is in. Subscribe if you want the universe explained the way it actually is. We begin. Christmas Day, 2021. A rocket lifted off from the jungle coast of South America and carried the most expensive telescope ever built into the sky. The James Webb Space Telescope cost $10 billion and took 30 years to build. It was folded up like origami inside the rocket, its mirror, its sunshield. Its entire body collapsed into a shape small enough to fit inside a launch vehicle. Then, piece by piece, over 29 days, it unfolded itself in space. Each step had to work perfectly. Engineers called those 29 days on the edge. There were 344 individual points where one failure would have ended everything. Nothing failed. Webb traveled 1 million miles from Earth to a location called the second Lagrange point. At that distance, the gravity of the Sun and Earth perfectly balance, so the telescope drifts in a stable loop without burning fuel. More importantly, out there it is cold. Webb needs the cold. It sees the universe in infrared light, which is essentially heat radiation. If the telescope itself were warm, its own glow would blind its instruments. So it carries a sunshield the size of a tennis court, 5 layers of material as thin as a human fingernail, blocking the light and heat of the sun, earth, and moon all at once. The mirror is 21 feet across, 18 hexagonal segments, each coated in a microscopically thin layer of gold. Not for looks, gold reflects infrared light at 98% efficiency, better than almost any other material on Earth. If you collected all the gold on those mirrors, it would weigh less than a golf ball. Engineers spent months aligning each segment to a precision smaller than a single wavelength of light. By July 2022, Webb was ready. The first images arrived at Mission Control in Baltimore, and scientists who had spent decades working toward this moment sat in silence. The images were sharper than anything Hubble had ever produced. They showed galaxies colliding, gas clouds igniting into stars, and the ghostly arcs of light bent around massive galaxy clusters by gravity itself. The universe looked richer, older, and stranger than anyone had prepared for. But something else was in those images. Something small, something that nobody had planned for. A team of astronomers in Australia was testing the early data. Their goal was straightforward: find the oldest galaxies Webb could detect. They looked at a patch of sky Hubble had already studied for years. They expected familiar shapes, familiar distances, familiar physics. Instead, they found 13 objects that made no sense, tiny, extremely compact, glowing a deep, specific shade of red that didn't match any known galaxy. Their brightness suggested enormous mass. Their color suggested enormous distance. When astronomer Ivo Labbé and his team ran the calculations, 6 of those 13 objects appeared to be nearly as massive as the Milky Way, existing less than 700 million years after the Big Bang. The universe was only 5% of its current age, and somehow, fully formed monsters were already there. The team checked the math 3 times. The answer didn't change. They published their findings in the journal Nature in February 2023, half afraid of what they had found. Other teams started looking at their own Webb data. They found more dots, then more, then hundreds. Every direction Webb pointed, the dots appeared. The universe had a secret, and it was written in red. The light hitting Webb's mirrors right now left its source before Earth existed. That sentence needs a moment. The Sun formed 4.5 billion years ago. Most of the little red dots Webb found existed 13 billion years ago. The light from those objects has been traveling through space ever since, crossing distances so vast that the universe itself has expanded during the journey. This is not a metaphor. It is the physical reality of how telescopes work. When you look at something far away, you are looking back in time. The farther the object, the older the light. A star 1 light year away looks the way it looked 1 year ago. A galaxy 13 billion light years away looks the way it looked 13 billion years ago. Webb is, in this sense, a time machine. But there is a complication. The universe has been expanding since the Big Bang. As light travels across that expanding space, the light itself stretches. The wavelength gets longer. Longer wavelength light shifts toward the red end of the spectrum, then past it into infrared light that human eyes cannot see at all. Astronomers call this effect redshift. The greater the distance, the greater the stretch, the redder the light becomes. This is exactly why Hubble, the telescope that launched in 1990 and spent decades producing the most famous space images in history, could never detect the little red dots. Hubble was built to see visible light and some ultraviolet. It was extraordinary at that job, but the ancient light from the universe's first few 100 million years had stretched so far into the infrared that Hubble was essentially looking with its eyes closed. Webb was built specifically to see infrared. Its gold-coated mirrors, its location 1 million miles from the warmth of Earth, its instruments cooled to temperatures colder than outer space itself. Every design choice existed to catch this stretched, ancient, heat radiation light. Picture it this way. The little red dots were always there in the universe's earliest era. Every other telescope we built just wasn't tuned to the right channel. Webb turned the dial, and suddenly those dots lit up by the hundreds. The color of an object in Webb's images tells astronomers two things at once: what the object is made of and how far away it is. Every chemical element absorbs and emits light at specific wavelengths, like a fingerprint. Hydrogen has its fingerprint. Oxygen has its fingerprint. Iron has 16 separate lines in a single spectrum, like a barcode. When Webb captures the light from a distant object and spreads it into a spectrum, scientists can read those fingerprints. They can measure exactly how much those fingerprints have shifted toward the red end of the dial. That shift tells them the object's distance and therefore its age. The calculation is precise enough that astronomers can place an object in time to within a few tens of millions of years across 13 billion years of cosmic history. The little red dots appeared in large numbers about 600 million years after the Big Bang. Their light is so old, so stretched, that no telescope before Webb could have even seen them. And hidden inside that ancient stretched light was a message. Scientists just had to learn how to read it. That reading would take 2 more years of argument, comparison, and one very lucky accident. But before the answer came, the dots themselves had to break something first. The first test images Webb sent back in June 2022 were never meant to be science. They were calibration data. Engineers were checking the instruments, making sure every sensor was aligned, confirming that the focus was right. The images were not supposed to contain discoveries. Then Ivo Labe's team in Australia looked at them anyway. The patch of sky they studied was a region Hubble had already photographed many times over many years. It was familiar territory. The team expected to find galaxies they already knew about, just sharper. Confirmation of existing data, nothing more. Within 48 hours, they had found 13 objects that challenged the timeline of the entire universe. 6 of those 13 glowing red blobs appeared to be massive, not just somewhat massive, nearly as massive as the Milky Way, which contains hundreds of billions of stars and took billions of years to build through mergers, collisions, and the slow accumulation of gas. These 6 objects seem to have achieved something close to that scale in a fraction of the time available. The universe, at that point 600 million years old, was a teenager. Gravity had been pulling gas together since the Big Bang, but the process was still new. Stars had only existed for a few 100 million years. The first galaxies were small, chaotic, fragile. They were nowhere near the size of the Milky Way. Labbe's team ran the numbers, then ran them again. The brightness of these objects, combined with their color and distance, pointed to enormous masses. The team published in Nature and waited for the response. The response came fast, and it was divided. Some astronomers were skeptical. They suggested the mass estimates might be off. Perhaps the objects were smaller and the brightness was caused by something other than stars, like the violent glow of a black hole feeding in the center. That would make the mass estimates meaningless. Others took the numbers seriously and started asking a harder question. If these objects really were as massive as they appeared, then everything scientists understood about how galaxies form in the early universe needed to be revised. One astronomer used the phrase, "a universe that is just too advanced for its age." There is a rule in cosmology. It is not a suggestion. It is baked into the mathematics of how matter clumps under gravity, how gas cools and collapses into stars, how stars build up inside galaxies over generations. That rule says large galaxies take a long time to form. You cannot rush it. The physics does not allow it, except, apparently, something was rushing it. Within weeks, other teams scanning Webb data found more red objects, then more. Not scattered and rare, but dense and abundant everywhere. One team estimated that the volume of early universe Webb was studying might contain 10 times more massive galaxies than the best models had predicted. That number, if true, meant something uncomfortable. Either the observations were wrong, or the models were wrong. Neither option is good when the models have been tested, refined, and validated for decades. The dots did not behave like new discoveries usually do, quietly, at the edge of detection, leaving room for doubt. There were hundreds of them, bright, repeating in every corner of the data. They demanded an answer, and the answer, when it came, would change what scientists thought these dots even were. By the end of 2022, the little red dots had stopped being a curiosity and become a crisis. A single anomalous object in astronomical data is easy to dismiss. Instruments malfunction, data gets corrupted. Strange one-off observations happen all the time and get filed away under unexplained without disturbing anyone's sleep. Science can absorb one mystery quietly. Hundreds of identical mysteries, repeating in every dataset, in every direction, is a different situation entirely. Teams around the world were independently analyzing Webb images from different surveys, different fields of sky, different instruments. None of them were coordinating. All of them found the same thing: tiny, compact, intensely red objects, appearing in the universe's earliest accessible era, then vanishing by about 1.5 billion years after the Big Bang. The pattern had 3 characteristics that made it impossible to brush aside. First, the abundance. Scientists estimated that for every cubic stretch of early universe they surveyed, there were far more of these objects than any existing model predicted. Some early estimates suggested the density was off by a factor of 10 or more. A factor of 10 in science is enormous. A factor of 2 might be a calibration error. A factor of 10 means something fundamental is wrong. Second, the consistency. The red dots showed up at roughly the same epoch in cosmic history every time. 600 million years after the Big Bang, they appear. 1.5 billion years after the Big Bang, they disappear. That kind of clean appearance and disappearance is the signature of a real physical process, not random noise or instrument error. Something in the universe was switching on and then switching off, right on schedule. Third, the brightness. These objects were extraordinarily luminous for their size. They looked compact in Webb's images, small points of light, yet they outshone many fully formed galaxies. Something was generating enormous energy inside a very small space. That combination, extreme brightness packed into extreme compactness, is what pointed scientists toward black holes before anyone had confirmed it. Black holes are the only objects known to produce that specific profile of energy. The scientific community began producing papers rapidly. By early 2024, Astronomers had compiled samples of hundreds of little red dots from various Webb surveys. One of the largest compilations, built from multiple surveys combined, contained objects that had all existed within the first 1.5 billion years of the universe's history. The team that produced that compilation found something that sharpened the mystery further. Many of the dots appeared to be spinning rapidly. Objects spinning that fast at that size carry enormous amounts of kinetic energy. That pattern matched what scientists see around black holes that are actively pulling in matter, not quiet black holes, but feeding ones, roiling and violent and bright. The dots were asking to be understood, and they were running out of patience. Up to this point, two explanations had been competing. Either these were gigantic galaxies that somehow assembled too fast, or they were black holes hiding inside something that looked like galaxies. Both explanations had problems. Both explanations required something to give. The problem with the galaxy explanation was about to become critical, because the early universe had very specific rules about how big anything could get in a very short time, and those rules were about to go under the microscope. Imagine building a skyscraper in a single afternoon. Every steel beam delivered, every floor poured, every wall raised and bolted in less time than a school day. Anyone who has watched construction knows that is physically impossible. Materials need time to arrive. Workers need time to work. Foundations need time to set. The early universe had the same problem, and the little red dots were, apparently, skyscrapers built in an afternoon. The Milky Way contains somewhere between 100 billion and 400 billion stars. It is a spiral structure about 100,000 light-years across, and it took billions of years to reach its current size. Gravity pulled gas clouds together. Those clouds collapsed into stars. Stars organized into clusters. Clusters merged and grew into larger systems over enormous stretches of time. The process is not fast. It cannot be fast. Gravity works at a set rate, and gas needs time to cool, collapse, and ignite. 6 of the 13 original red blobs appeared to have masses approaching the Milky Ways, and they existed when the universe was only 600 million years old. The universe itself is about 13 billion years old today. At 600 million years, it was roughly 4% of its current age. Picturing that in human terms, imagine a person who weighs as much as a fully grown adult, but is only 2 years old. The standard model of galaxy formation, built from decades of observations, computer simulations, and mathematical physics, said this could not happen. The model predicts how fast matter can collapse under gravity given the density of the early universe, the temperature of the gas, and the absence of the heavy elements that help gas cool faster. The math produces a speed limit, and the little red dots appeared to be breaking it by a wide margin. Some astronomers began calling this the impossible galaxies problem. A few papers used the phrase, too big, too soon. If the objects really were massive galaxies, it would require significantly more star formation in the very early universe than any model had accounted for. The models would need to be rebuilt from the ground up. This matters beyond academic interest. The model of galaxy formation is not just a theory about galaxies. It is tied to the model of how dark matter clusters, how the universe expanded after the Big Bang, and how the large-scale structure of the cosmos, the web of galaxy filaments and voids visible today, came to exist. Pull on one thread, and the entire fabric shakes. The saving possibility was the alternative explanation. These weren't galaxies at all. Their light wasn't coming from hundreds of billions of stars. It was coming from a single, incredibly violent object in the center. A black hole eating so much material so quickly that it outshone everything around it. If that were true, the mass estimates were wrong. The dots could be much smaller galaxies hosting intensely active black holes. The size problem would dissolve, the models would survive, but that explanation had its own problems too. Problems that would take 2 more years and a very specific scientific tool to finally untangle. Before that tool was used, scientists needed to understand something fundamental. What rules, exactly, was the early universe playing by, and why were those rules so strict? The Big Bang did not produce stars. It produced light, heat, and two elements, hydrogen and helium. That was it. The entire periodic table that exists today, every carbon atom in your body, every iron atom in your blood, every oxygen atom in every breath you take, did not exist yet. The universe had to build all of it from scratch. For the first few 100 million years, the universe was a sea of hydrogen and helium gas, slowly cooling as it expanded. No stars, no planets, no heavy elements. Astronomers call this era the Cosmic Dark Ages. The universe was dark because there was nothing yet to produce starlight. Then, around 200 million years after the Big Bang, gravity started winning. Dense patches in the gas cloud grew denser. Eventually, a patch would collapse far enough that the pressure in the center became hot enough to ignite nuclear fusion. The first star lit up, then another, then another. The Cosmic Dark Ages ended. These first stars were enormous by today's standards. Some may have been 1,000,000 times the mass of the Sunday. They burned through their fuel fast, lived for only a few million years, and died in massive explosions. Those explosions scattered the first heavy elements, carbon, oxygen, silicon, into the surrounding gas. That seeding of heavy elements is crucial. Heavier elements are better at radiating heat away from collapsing gas clouds. Faster cooling means faster collapse. Faster collapse means faster star formation. The more heavy elements a region of space has, the faster galaxies can grow. The early universe, before those first stars exploded, had almost none of these elements. It was working with pure hydrogen and helium, which cools slowly and collapses slowly. This is why the Standard Model puts a speed limit on galaxy formation. In the earliest era, the ingredients for fast growth were simply not there yet. The speed limit is also connected to dark matter. Dark matter makes up roughly 85% of all matter in the universe. It does not emit light, does not absorb light, and cannot be directly detected. Its presence is inferred from the way it bends light and pulls on visible matter around it. Dark matter formed the scaffolding on which galaxies were built. It clumped first, and gas followed, pouring into the gravitational wells dark matter created. But dark matter clumped slowly too. In the early universe, those wells were shallow. Gas trickled in at a rate set by physics. Building a massive galaxy required billions of years of accumulation. All of this meant the little red dots, if they were truly massive galaxies, were doing the impossible. They had somehow leapt over every bottleneck the early universe had placed in front of them. There was a third possibility, one that was harder and stranger, a process called direct collapse. Instead of forming stars first and building galaxies slowly, a massive cloud of gas collapses directly into a black hole in a single catastrophic event. No stars, no slow accumulation, just sudden, violent implosion. That process, if real, could produce a black hole in a fraction of the time a galaxy needs to form. And if that black hole then fed furiously on the gas surrounding it, it would glow. It would glow red. It would look exactly like a little red dot. The question was whether direct collapse was actually possible, and the answer would come from simulations that were only just being run. By early 2023, the little red dots had the astronomy community split into 3 camps, and the arguments between them were running hot. Camp 1 held that the dots were massive galaxies. The mass estimates were real, the timeline was uncomfortable, and the Standard Model needed updating. Some in this camp argued that galaxy formation in the early universe was simply more efficient than anyone had modeled. Perhaps the gas cooled faster than expected. Perhaps dark matter halos formed denser concentrations than simulations had produced. The model needed tuning, but not replacement. Camp 2 held that the mass estimates were wrong. The brightness wasn't coming from billions of stars. It was coming from a single source, a growing black hole in the center of a much smaller galaxy. Active black holes, known as active galactic nuclei, can outshine their entire host galaxy. If the little red dots were just active galactic nuclei seen from an extreme distance. The apparent mass problem disappeared. The galaxies could be normal-sized. Only the black hole was exceptional. Camp 3 was the smallest and the most radical. These researchers proposed something had never been directly observed before, a new class of object entirely. Giant spheres of extremely dense gas, powered at their cores by rapidly feeding black holes, mimicking the appearance of a star. Some called them black hole stars. The outer gas would behave like a stellar atmosphere, glowing and pulsing. The inner black hole would provide the energy. From 13 billion light-years away, Webb would see something that looked like neither a galaxy nor a known star. Each camp had evidence. Each camp had problems. The galaxy camp struggled with the timeline. The active galactic nucleus camp struggled with the fact that the dots lacked the X-ray brightness that feeding black holes typically produce. When scientists pointed X-ray telescopes at the little red dots, most of the dots were nearly silent. Active black holes are usually loud in X-rays. These weren't. Something was blocking or absorbing the X-rays before they could escape. The black hole star camp struggled with the fact that nothing like this had ever been confirmed. Scientists prefer explanations rooted in known physics. A brand new class of object requires extraordinary evidence. What all three camps agreed on was this: the standard picture of the early universe was incomplete. Whatever the dots were, their sheer abundance meant the cosmos had been doing something in those first few 100 million years that no existing model had captured, and the fact that they all vanished after 1.5 billion years meant that whatever they were doing, they stopped doing it on a cosmic schedule. Two tools would eventually break the deadlock. One was patience. 2 years of continuous, methodical comparison of hundreds of dots by a team in Copenhagen. The other was an accident, a single dot that happened to be sitting behind a galaxy cluster at precisely the right angle, magnified by the cluster's gravity, to a level of detail no other dot had ever been examined at. Both lines of investigation were running in parallel in 2023. Neither team knew yet what they would find, but the picture they were about to assemble would explain not just what the dots were, but what they meant for the entire history of the universe. First, though, the science needed to explain one basic thing that had not been addressed yet. What exactly does red mean when astronomers say a distant object is red? Because the answer is stranger and more specific than it sounds. Hold a glass prism up to sunlight, and a rainbow spreads across the wall. The white light splits into its ingredients: red, orange, yellow, green, blue, violet. Each color is a different wavelength of light. Shorter wavelengths are blue, longer wavelengths are red. This spread of wavelengths is called a spectrum. Every object in the universe produces its own version of this spread. Hot objects produce more blue light. Cool objects produce more red. Dense objects produce smooth rainbows. Thin gas clouds produce only specific lines of color, bright spikes at exact wavelengths that correspond to specific chemical elements. Hydrogen emits light at a specific set of wavelengths. Heat hydrogen gas, and it glows at those exact wavelengths every time, anywhere in the universe. Same for oxygen, same for helium, same for iron. Each element has a signature pattern of lines, like a fingerprint, that appears at the same positions in the spectrum, no matter where in space you look. This system allows astronomers to identify what a distant object is made of without ever physically reaching it. They spread its light into a spectrum and read the fingerprints. But here is where it gets more powerful. Because the universe is expanding, light from distant objects stretches during its journey to us. That stretching shifts all the fingerprints toward longer wavelengths. Toward the red. The greater the distance, the greater the shift. Astronomers measure how far each fingerprint has moved from its expected position, and that measurement, called the redshift, tells them exactly how far away the object is, and therefore how old the light is. A redshift of 1 means the wavelengths have doubled in length. A redshift of 6 means they have stretched to 7 times their original length. The little red dots that first appeared in the 2022 Webb data had redshifts ranging from around 5 to as high as 10. That places them between about 500 million and just over 1 billion years after the Big Bang. The light from these objects has stretched so far during its journey that it passed through all visible colors and landed deep in the infrared, invisible to human eyes, invisible to Hubble, perfectly matched to Webb's instruments. This is why the dots look red in Webb's images. The infrared light Webb detects gets displayed as red on the images scientists publish. The redness is not just a color, it is a direct measurement of age and distance. But the dots were unusually, specifically red. Their color was not just the result of age and distance. Something about the objects themselves was producing more infrared light than expected. The spectrum had a shape that didn't match a normal galaxy. It didn't match a known quasar. It had a deep dip in it, a dropout in the spectrum at a specific wavelength called the Balmer break that was puzzling researchers deeply. The spectrum was like a song with a note missing in the middle. Every attempt to explain the song required explaining why that note was gone. Understanding the spectrum required something Webb had not yet applied to enough of these objects: dedicated, deep spectroscopic observation, not just images, not just color, actual, detailed, light-splitting analysis of individual dots. That campaign was already underway, and the first results from it were about to shake the entire debate loose. The dots were red. Scientists knew that. But knowing a color and knowing what causes a color are completely different problems. There are several ways an object can appear red to a telescope like Webb. The simplest is distance. As explained, light from the early universe stretches into the infrared, and Webb displays infrared as red. Most distant objects have some redness for this reason alone, but the little red dots were redder than expected for their distance. Their spectra showed a very specific shape, bright at longer infrared wavelengths, dropping off steeply at shorter wavelengths. This shape is called a red continuum, and in normal astronomical objects, it usually means one of two things. Either the object contains a lot of dust, which blocks shorter wavelengths of light, or the object's gas is very hot and very dense in a specific way. Dust was the first guess. Dusty galaxies are known to have red spectra. When stars form in regions packed with gas and dust, the dust absorbs short wavelength ultraviolet light from the young stars and re-emits it as longer wavelength infrared. This process, called reprocessing, is well understood and well documented. The problem was the scale. For dust to produce the observed redness at that distance, the dots would need to contain enormous amounts of it. Young galaxies in the early universe have very little dust. Dust is made of heavy elements, and the early universe had barely produced any. The numbers required more dust than the early universe could plausibly have generated. Dust alone couldn't be the answer. The next candidate was the dense ionized gas cocoon. As researchers began developing the black hole star model, they realized that a sufficiently thick, hot cloud of ionized gas around a feeding black hole would do something specific to the light passing through it. High-energy radiation from the black hole, ultraviolet and X-ray light, would be absorbed by the inner layers of the cocoon and re-emitted as lower-energy light. Shorter wavelengths converted into longer ones. The result would look red, very specifically, precisely, consistently red. The way the little red dots looked, the cocoon model also explained something else that had been nagging at scientists. The dots showed extremely broad emission lines in their spectra. Emission lines are those fingerprint spikes produced by glowing gas. Normally those spikes are sharp. In the little red dots, they were smeared wide, as if the gas producing them was moving at enormous speeds in every direction simultaneously. Gas moving that fast, that chaotically, in multiple directions, is the signature of gas caught in the gravity well of a black hole, racing inward and outward in a turbulent feeding event. Broad emission lines show up in known active black holes. The dots had them, broad and smeared and fast. That was a signal pointing clearly toward a black hole, not toward a galaxy full of quiet stars. But the dots were also unusually compact. Galaxies with hundreds of billions of stars take up space. The dots were tiny pinpoints, barely resolved even in Webb's sharp images. Something was generating enormous energy in an extremely small volume. Everything was pointing the same direction. But pointing is not proving. What the field needed was a spectrum detailed enough to test the cocoon theory directly, line by line, fingerprint by fingerprint. That spectrum was closer than anyone knew, and the team about to obtain it would spend 2 years earning the right to read it. For 30 years, the Hubble Space Telescope was humanity's sharpest eye on the universe. It orbited 340 miles above Earth, above the blurring of the atmosphere, and produced images so clear and deep they reshaped every field of astronomy. Hubble found galaxies at extreme distances. Hubble measured the expansion rate of the universe. Hubble revealed the era when star formation peaked and the era when it began to decline. Hubble never found a single little red dot. That absence tells a precise scientific story. Hubble was built to see invisible light and a portion of ultraviolet. Its instruments were calibrated for wavelengths between roughly 0.1 and 2.5 micrometers, with its sharpest sensitivity in the visible range that human eyes can also see. That range covers most of the light produced by nearby and mid-distance galaxies with precision. But for objects at the extreme distances of the little red dots, redshifts of 5, 6, 7, and higher, the light has stretched far beyond what Hubble's instruments were designed to capture. The fingerprints of hydrogen, the most common element in the universe, appear at a wavelength of around 0.12 micrometers in their rest frame. By the time that light reaches us from an object at redshift 6, it has stretched to around 0.85 micrometers, still visible to Hubble, but dim. The continuum light of the object, the overall glow of the whole system, not just the spectral lines, stretches even further into the mid-infrared range, around 2 to 4 micrometers. Hubble's instruments fall off steeply at those wavelengths. The signal is still there, technically, but it drowns in instrument noise. Hubble missed the dots because it was essentially colorblind to the wavelengths the dots were brightest in. Webb was designed around this exact problem. Its gold mirror was not a stylistic choice. Gold reflects infrared light more efficiently than any other coating material. Its detectors were cooled to minus 448 degrees Fahrenheit, colder than any natural environment in the solar system, to eliminate the thermal noise that would otherwise swamp a faint infrared signal. Its sunshield wasn't just a heat protector, it was what made the instruments cold enough to work. Every engineering decision in Webb's 30-year design process was optimizing for infrared sensitivity at the wavelengths where the early universe's light had landed. The fact that Hubble saw nothing where Webb saw hundreds is not a failure of Hubble. It is confirmation that Webb's technology opened a genuinely new window. Telescopes don't just see farther, they see differently. Each new wavelength range reveals a universe that was invisible before. Astronomers have known since the planning stages of Webb that there would be surprises at infrared wavelengths. Every new wavelength range in history has produced surprises. X-ray telescopes revealed violent processes invisible to optical instruments. Radio telescopes revealed galaxy jets and the cosmic microwave background. Infrared telescopes on the ground had already hinted that the early universe was active in ways visible light couldn't fully capture. Webb confirmed that completely, and the something it revealed, these hundreds of glowing red dots scattered through the infant universe, turned out to be something even Webb's builders hadn't specifically anticipated. That something was about to get a name, a mechanism, and a team willing to spend 2 years chasing it down. In the summer of 2022, as the first Webb images arrived, a group of researchers at the Niels Bohr Institute in Copenhagen sat down with a specific question. What, exactly, were the red dots? The Cosmic Dawn Center, based at the Niels Bohr Institute, was built for precisely this kind of investigation. Its researchers specialized in the earliest era of the universe, the period between the Big Bang and the first billion years, when stars, galaxies, and black holes were just beginning to organize themselves out of raw gas. They had spent years preparing for Webb's data, building analysis tools, calibrating expectations. What they had not prepared for was the scale of the confusion the dots created. Professor Darrach Watson led one of the core investigations. He and his team began a systematic, methodical study of the dots using Webb data, accumulating spectra, those detailed light fingerprints from hundreds of objects over the course of nearly 2 years. By early 2024, the team had collected spectra from around 4,500 distant galaxies, one of the largest spectroscopic datasets ever assembled with a space telescope. That campaign required nearly 60 hours of Webb observation time, a significant allocation for a telescope that is in extraordinarily high demand from researchers worldwide. The work was not glamorous. Reading a spectrum is a precise, slow process. Each spectral line has to be identified, measured, and compared against libraries of known atomic and molecular signatures. The broadening, the shape, the ratios between different lines, all of it carries information, and all of it has to be extracted carefully to avoid misreading the data. What the Copenhagen team kept finding was that the dots were strange in a consistent way. Their spectra had very broad emission lines, lines smeared wide by gas moving at speeds of several thousand miles per second in every direction simultaneously. They had deep red colors that dust alone couldn't explain, and they were nearly silent in X-rays, which was deeply puzzling if they housed actively feeding black holes. Then, in July 2024, the team found one specific object that stood out from all the others. Its spectrum showed an enormous amount of mass concentrated in an extremely small volume. It became the most extreme example of what the dots represented, and it hardened the team's emerging conclusion. These were black holes, not galaxies. Young, feeding, violent black holes wrapped in dense cocoons of ionized gas. The Copenhagen team published their conclusion in Nature in January 2026. 2.5 years of continuous work written into a single paper. Their answer reshuffled the entire debate. The dots were real objects. They were explainable by physics already known, and they had been waiting in the data the whole time for exactly this kind of sustained, careful, patient analysis. But patience wasn't the only tool that cracked the case. Across the Atlantic, a researcher at the University of Texas was looking at a single dot through an accidental natural magnifying glass, and what he found inside it made everyone else's data suddenly click. The core idea behind the cocoon theory is both simple and violent. A young black hole, wrapped in a thick, hot cloud of its own gas, feeding furiously, glowing through the cloud like a light bulb inside a frosted glass globe. The cloud is not a gentle nebula. It is ionized gas, meaning the gas is so hot that the electrons have been stripped from their atoms. The temperature inside is in the millions of degrees. The density is extreme, far more packed than the diffuse clouds normally found around galaxies. And the source of energy driving all of it is the black hole at the center, pulling in material and converting a fraction of it directly into radiation. Here is how that energy production works. As gas falls toward a black hole, it does not fall straight in, it spirals. The gas forms a disk around the black hole, and as it spirals inward, it compresses and accelerates. Particles slam into each other at enormous speeds. The friction generates heat. The heat generates light. By the time the gas reaches the inner edge of that disk, it is radiating at temperatures of many millions of degrees, producing light across the entire spectrum from radio waves to X-rays. This process is called accretion. It is the single most efficient known method of energy release in the universe. Nuclear fusion, the process that powers stars, converts less than 1% of a hydrogen atom's mass into energy. Accretion onto a black hole can convert up to 10% of infalling matter into pure energy. A feeding black hole, pound for pound, is about 10 times more energetic than a star. In the case of the little red dots, The black hole sits inside a cocoon of dense, ionized gas. The X-rays and ultraviolet light produced by accretion hit the inner wall of the cocoon and get absorbed. The cocoon then re-emits that energy at lower wavelengths, longer wavelengths, less energetic, redder. This is the process scientists call reprocessing, and it explains both the red color of the dots and their silence in X-ray detectors. The X-rays never escape. They are converted into infrared light before they can get out. The cocoon also explains why the emission lines in the dot's spectra are so broad. The gas in the cocoon is in motion in every direction, some parts falling inward, some parts being blown back outward. Gas moving toward Webb, when it emits light, produces slightly shifted lines. Gas moving away produces lines shifted the other way. The result is a smeared, broadened line. The width of that smearing tells scientists how fast the gas is moving and how dense it is. The numbers that came out of those measurements were startling. The cocoon gas was moving at speeds consistent with the gravitational pull of a black hole weighing up to 10 million times the mass of the Sunday. The density of the ionized cocoon was so high that light could not travel through it in a straight line. It had to scatter repeatedly through electrons before escaping. That repeated scattering, called electron scattering, left a specific signature in the line shapes that the Copenhagen team identified clearly in their spectra. This was not guesswork. These were measurements, matched against physical models, line by line, and every measurement pointed to the same picture: young black holes, eating fast, hidden inside their own glowing clouds. But one thing still wasn't clear. If these black holes were so massive and so violent, how did they get there so fast? Where did they come from? The answer required going further back in time than even the dots themselves, to the very first moments when black holes began forming in the infant universe. Picture a bathtub draining. Water spirals toward the plug hole, moving faster as it gets closer. The spiral forms because of the water's momentum, carrying it sideways as gravity pulls it down. The same thing happens when gas falls toward a black hole, but at a scale and violence that makes a bathtub drain look peaceful. The gas that feeds an early black hole comes from the surrounding cloud. It starts as diffuse material far from the black hole's center. Gravity pulls it inward, but the gas carries momentum in a random direction, so instead of falling straight in, it begins to spiral. As more gas spirals from many directions, the streams of infalling material flatten into a disk, the accretion disk, rotating around the black hole like an enormous spinning plate. As the gas moves inward through this disk, it loses energy through friction. Particles in the disk collide with each other. Those collisions convert orbital energy into heat. The closer to the black hole, the faster the orbit, the more violent the collisions, the hotter the gas. The innermost ring of the disk reaches temperatures measured in the tens of millions of degrees. At those temperatures, matter doesn't just glow, it screams. The screaming takes the form of radiation at every wavelength simultaneously. Gamma rays, X-rays, ultraviolet, visible light, infrared. The accretion disk around an actively feeding black hole is among the most luminous things in the known universe. A single feeding black hole can outshine an entire galaxy containing hundreds of billions of stars. But not all the gas makes it to the event horizon. Black holes are, as Professor Derek Watson put it, messy eaters. As gas spirals inward and heats up, some of it reaches temperatures and pressures high enough to be blasted back outward. The black hole's magnetic field, twisted and amplified by the spinning disk, launches jets of material from the poles at nearly the speed of light. These jets punch through the surrounding gas cloud and shoot into open space. Meanwhile, radiation pressure, the physical push that light exerts on matter, drives outflows of gas from the outer edges of the disk. This material gets blown back into the cocoon and sometimes beyond it, carrying energy outward and heating the surrounding environment. In the little red dots, this entire violent cycle was happening inside an unusually dense cocoon. The jets and outflows were captured, absorbed, or scattered back inward by the surrounding gas before they could escape cleanly. The X-rays from the innermost disk were soaked up by the cocoon and re-emitted as infrared. The gas that was blown out looped back and added to the cocoon. This created a feedback loop. The black hole was eating the cocoon. The cocoon was containing the radiation. The radiation heated the cocoon, which thinned it slightly at the outer edges while remaining dense at the inner ones. Over time, the cocoon would shrink. The black hole would eventually run low on food. The intense glowing phase would end. This mechanism is precisely why the little red dots vanished. They didn't disappear because the black holes died. They disappeared because the cocoon was consumed. The black hole went quiet, at least in the wavelengths Webb was watching, and the dots faded from the universe's visible record around 1.5 billion years after the Big Bang, right on the schedule the data showed. But there was still a piece missing. The cocoon's gas was described as ionized. That word needs unpacking, because understanding it changes how the entire picture looks. Atoms are mostly empty space. Picture a grain of sand sitting in the middle of a football field. That grain of sand is the nucleus of a hydrogen atom. The stands and parking lot beyond the field, that is where the single electron orbits. The atom is almost entirely nothing, with two tiny physical things connected by an electrical force across a vast interior void. Normally, that electron stays in orbit. It can be pushed to a higher orbit by absorbing energy, or it can drop back down and release a burst of light, but it stays with its nucleus. That is a neutral atom. Ionized means the electron has been knocked off entirely. To ionize hydrogen, you need heat or radiation energetic enough to rip the electron free. The temperature required is around 18,000 degrees Fahrenheit. Once that electron is gone, the nucleus is a bare proton, carrying a positive charge with nothing to balance it. The free electron carries a negative charge and wanders independently. The gas is now a plasma, a mixture of free nuclei and free electrons, all electrically charged, all interacting with light in ways neutral gas does not. A plasma is not just hotter gas, it is physically different from neutral gas. It conducts electricity, it responds to magnetic fields, and most importantly for understanding the little red dots, it scatters light. When a photon, a particle of light, travels through ionized gas and hits a free electron, it bounces. The direction changes. The energy is slightly redistributed. Then it hits another electron and bounces again. In a dense enough plasma, a single photon might scatter thousands of times before escaping. Each bounce slightly shifts the photon's wavelength. The result, when many photons scatter through many electrons, is a characteristic broadening and reshaping of spectral lines. This specific signature, called electron scattering broadening, is what the Copenhagen team found in the spectra of the little red dots. The emission lines were not just broad because gas was moving fast in different directions. They were broad because light was being scattered through an incredibly dense ionized cocoon before escaping. The density required to produce that amount of scattering is extreme. Scientists measured it and found that the cocoon was so dense that light was spending roughly a day's worth of travel time just crossing the region immediately around the black hole. For reference, a region that light crosses in one day is about 16 billion miles across. The cocoon was compact and extraordinarily packed. This extreme density also explained one of the other mysterious features of the dots: why they appeared to have very little dust. Dust molecules cannot survive in a plasma that hot and that energetic. They are torn apart. The absence of dust signatures in the spectra, which had confused researchers early on, was actually consistent with the cocoon model. The environment was too violent for dust to form or persist. The ionized cocoon was not a side effect. It was the mechanism. It transformed the raw violence of a feeding black hole into the specific glowing red object that Webb detected across 13 billion years of space. Understanding the cocoon as a physical structure changed everything about how scientists read the spectra. The missing X-rays, the red color, the broad lines, the absence of dust, all of it fit into a single coherent picture. And that picture was about to get its sharpest test yet. From a single object caught behind a galaxy cluster at exactly the right moment, in exactly the right position. When the little red dots were first measured, astronomers estimated their masses using their brightness. Brighter object, more mass, that was the logic. And the brightness suggested enormous masses, billions of times heavier than the Sunday. That estimate put the dots in a category of objects called ultramassive black holes. Things so heavy they challenged every theory of how black holes grow in the early universe. Those estimates were wrong, and the reason they were wrong matters enormously. The mass estimate based on brightness assumes that the radiation is coming from stars. A galaxy with a certain brightness is assumed to contain a certain number of stars, and the total mass of those stars gives you the mass of the galaxy. That calculation works well for normal galaxies. But the little red dots were not normal galaxies. Their light was coming almost entirely from one thing: the accretion disk around a feeding black hole. A single black hole can outshine an entire galaxy's worth of stars. Using the brightness of that black hole to estimate the mass of a galaxy, the way you'd estimate it for a star-filled system is like using the brightness of a single spotlight to estimate the population of a city. When the Copenhagen team modeled the dots as black hole cocoon systems instead of galaxies, the mass picture changed completely. The black holes responsible for the observed brightness turned out to be up to about 10 million times the mass of the Sunday. That sounds large, but compared to the earlier estimates of billions of solar masses, it is 100 times lighter. The correction was enormous. 10 million solar masses is still a supermassive black hole by any definition. The black hole at the center of the Milky Way weighs about 4 million solar masses. The little red dots black holes were in the same neighborhood. Heavy, yes, but heavy in a way that fits within the universe's timeline. A black hole of 10 million solar masses, formed from direct collapse or from the first generation of massive stars, could plausibly reach that size within 600 million years without violating any known physics. This is what Professor Watson described as the relief of the discovery. Scientists had been worried that the dots required exotic new explanations, new physics, a broken model. The corrected mass estimate removed that pressure. The universe was doing something extreme, yes, but it was doing it with tools it already had. The violence was intense, but it was comprehensible violence. There was another consequence to the lower mass estimate. If the black holes were smaller than previously thought, the galaxies hosting them could also be smaller. The impossible galaxy problem galaxies too massive to exist so early softened considerably. The galaxies hosting these black holes could be modest, immature systems. It was just their central black holes that were furiously active, making the whole system look far more massive than it actually was. The picture was clarifying. Young, hungry black holes, dense ionized cocoons. Red light filtered through plasma. Masses large but within reach of known formation mechanisms. But one deep mystery remained. If these black holes were heavy but not impossibly heavy, they still needed to have formed from something. They needed seeds. And those seeds pushed the question back to the very beginning of the universe, to the first stars, the first gas clouds, and possibly to the dark matter itself. What happened in the first few 100 million years that planted the seeds of these violent objects? The answer is strange, and partly still unresolved. Active black holes are usually loud. When a black hole feeds aggressively, the inner region of its accretion disk heats to temperatures in the tens of millions of degrees. At those temperatures, gas emits X-rays in enormous quantities. X-ray telescopes have been finding these signals for decades. Known feeding black holes, called active galactic nuclei, or quasars, light up X-ray maps of the sky like beacons. The X-ray brightness of a feeding black hole is so reliable a signal that astronomers routinely use X-ray surveys to catalogue active black holes across the universe. The little red dots were almost completely invisible in X-rays. That silence was one of the most puzzling features of the dots from the beginning. If they housed feeding black holes, why weren't they screaming in X-rays? If they weren't feeding black holes, what was producing the broad emission lines, the red continuum, the enormous energy output? Nothing else known in astronomy produces that combination of features without also producing strong X-ray emission. The cocoon model solved this problem directly, and in doing so, it turned the silence from a mystery into a measurement. The ionized gas cocoon surrounding the black hole is extremely dense enough that X-ray photons produced in the innermost disk cannot travel through it without being absorbed. X-rays are high-energy, short-wavelength photons. When one enters the cocoon's dense plasma, it collides with the free electrons and ions there, and it transfers its energy to them. The plasma heats up slightly. The X-ray photon is absorbed. The energy is then re-emitted at lower frequencies, longer wavelengths, less energetic, in the infrared. The cocoon is, in this sense, an X-ray shield. It soaks up every X-ray from the inner accretion disk and converts it to infrared light before it can escape into open space. From the outside, the object looks X-ray quiet while being infrared bright, exactly what the little red dots showed. The thickness of cocoon required to absorb that much X-ray emission is measurable. Scientists call it the column density, the number of charged particles per square inch that an X-ray has to pass through before escaping. The measurements from the dot spectra indicated column densities high enough that even hard X-rays, the most penetrating kind, could not punch through the cocoon cleanly. This also predicted something scientists could test. If they pointed the Chandra X-ray Observatory, the most powerful X-ray telescope ever built, at a little red dot and stacked many hours of exposure, they should see not silence, but a faint, filtered X-ray glow. The X-rays produced deep inside the cocoon should not all be absorbed. Some fraction should scatter at angles that allow partial escape. It would be dim, but it would be there. When teams combined Webb and Chandra observations of the same dots, they found exactly that. Faint, soft X-ray signals, consistent with the predictions of the dense cocoon model. The silence wasn't total, it was muffled, and the degree of muffling matched the cocoon densities calculated from the infrared spectra. The missing X-rays had become confirmation. Every strange feature of the little red dots, the red color, the silent X-rays, the broad lines, the compact size, was now explained by a single, unified, physical picture. A young, dense, furiously feeding black hole wrapped in its own exhaust. But one question remained, still nagging, still unanswered. Where did all the dots go? The little red dots kept a schedule. They appeared in large numbers around 600 million years after the Big Bang. They were most abundant between 600 million and about 1 billion years after the Big Bang. Then, between 1 billion and 1.5 billion years, their numbers dropped sharply. By 1.5 billion years after the Big Bang, they were effectively gone. Later, Webb images, from that period onward, showed none of the characteristic compact red sources. A population of objects appearing and vanishing on a cosmic schedule is a strong signal. It means whatever process created them was active during a specific window, ran its course, and ended. The dots were not a permanent feature of the universe. They were an era. Understanding what ended that era requires understanding what maintained it. The cocoon model provides the answer. Each little red dot was a young black hole consuming its surrounding gas cocoon. The cocoon was both the fuel and the glowing shell that made the dot visible. As the black hole ate, the cocoon shrank. As the cocoon shrank, the fuel supply decreased. As the fuel supply decreased, the accretion rate dropped. As the accretion rate dropped, the system became less luminous. The red glow faded, and the dot disappeared from Webb's detectable range. Think of a coal fire. While the coal burns, it glows orange-red and puts out enormous heat. The moment the coal runs out, the glow vanishes. The fire didn't die because something extinguished it. It died because it consumed everything available to it. The black holes did not die. They survived. They still exist today, grown larger, quieter, sitting at the centers of galaxies. They became the supermassive black holes that anchor every large galaxy in the modern universe, including the one at the center of the Milky Way. The visible, glowing, cocoon-surrounded phase simply ended when the fuel ran out. The timing of the disappearance also ties to something broader happening in the early universe around 1 to 1.5 billion years after the Big Bang. During that period, the universe went through a phase called reionization, when radiation from early stars and active black holes stripped the electrons from hydrogen gas across enormous stretches of space. As the intergalactic gas changed state, conditions for forming extremely dense, localized cocoons became less favorable. The raw material the black holes needed to maintain their glowing shells was becoming more diffuse, more spread out, less concentrated. The combined effect black holes eating through their cocoons and the broader environment becoming less hospitable to cocoon formation produced the sharp drop-off in dot numbers that Webb measured. What replaced the dots was quieter but more familiar. After 1.5 billion years, the universe began showing the forerunners of galaxies as we know them today, more structured, more extended, centers already containing the supermassive black holes that had just finished their furious early growth phase. The dots were a larval stage, a brief, violent, necessary phase in the development of the cosmic structures that now surround us on all sides. And that transition, from violent infant black hole to quiet galactic center, was only the beginning of what the discovery implied, because the question of how those black holes formed in the first place, what seeded them, and what role they played in building the galaxies that followed them was about to pull the investigation into territory far stranger and more profound. The little red dots were not accidents. They represented a specific, necessary phase in the life of a young black hole, a phase that had been predicted in theory for years, but never directly seen until Webb turned its gold mirrors toward the infant universe. To understand why this phase had to exist, consider the problem black holes face in the early universe. A black hole that forms from the collapse of a massive star starts out with a mass of perhaps 10 to 100 times that of the Sunday. The supermassive black holes scientists find at the centers of large galaxies today weigh millions or billions of solar masses. Getting from 100 solar masses to 1 billion solar masses in less than a billion years requires growing at an extraordinary rate, almost continuously, without long breaks. The mathematics of black hole growth sets a speed limit called the Eddington limit. This is the maximum rate at which a black hole can eat before the radiation it produces pushes back hard enough to blow the infalling gas away, starving itself. At the Eddington limit, a black hole roughly doubles its mass every few tens of millions of years. To get from stellar mass to supermassive within a billion years, a black hole needs to stay near or above that limit almost the entire time. Staying at that limit requires a continuous, dense fuel supply. Open space does not provide that. Gas in the broader universe is too spread out, too diffuse, too easily disrupted by radiation pressure. The black hole would eat quickly, then run out of gas in its immediate vicinity, then wait while new gas slowly drifted in, then eat again. Start, stop, start, stop. That kind of interrupted feeding is too slow to explain the supermassive black holes found in the early universe. The cocoon solves this. An extremely dense cloud wrapped tightly around a young black hole provides the continuous, concentrated fuel supply that a rapidly growing black hole needs. The gas is right there, close, dense. The black hole can eat without interruption, staying near or above the Eddington limit for millions of years straight. The cocoon is, in Professor Watson's words, the fuel tank that makes the growth spurt possible. This is what Watson meant when he said, "We have captured the young black holes in the middle of their growth spurt at a stage that we have not observed before." Before Webb, this phase had been a theoretical necessity. Scientists knew something had to account for the rapid early growth of supermassive black holes, but no telescope had ever caught it happening. The little red dots were that process, visible, measurable, and spread across hundreds of objects. The growth spurt phase is brief by cosmic standards, a few 100 million years at most. But it accomplishes something that everything coming after it depends on. It takes a relatively modest black hole and drives it to supermassive scale before the cocoon runs out. After the growth spurt ends, the black hole can grow more slowly, through mergers and occasional feeding events, without needing the intense, continuous accretion that the cocoon provided. The dots were the universe speed-running the early development of its most massive objects, and that speed-run had a starting point that required its own explanation, because the seeds from which these black holes grew did not form in the same way as the black holes scientists know from stellar collapse. Something different and far more dramatic created them. Science moves slowly. Then, occasionally, it moves fast because something lands in your lap that nobody planned for. In late 2023, a team of astronomers at the University of Texas at Austin was running a Webb observation program called GLIMPSE. The primary goal was to study the galaxy cluster known as Abell S 1063, a massive structure containing hundreds of galaxies sitting about 4 billion light-years from Earth. The team was searching for population 3 stars, the hypothetical first-generation stars of the universe, and for faint background galaxies magnified by the cluster's gravity. Tucked into the data, behind the cluster, was a small red object, unremarkable at first glance. Identified by catalogue number, it would come to be called GLIMPSE 17775. What made this dot special had nothing to do with the dot itself. It had to do with geometry. GLIMPSE 17775 sits behind Abell S 1063 from our perspective on Earth. That means the massive galaxy cluster is positioned between us and the dot, along nearly the same line of sight. Massive objects bend the light that passes near them, a phenomenon called gravitational lensing, predicted by Einstein's general theory of relativity and confirmed observationally for nearly a century. A galaxy cluster as massive as Abell S 1063 acts as a natural magnifying glass, bending and amplifying the light from objects behind it. In this case, the cluster magnified the light from GLIMPSE 17775 by a factor that made Webb's 30-hour observation of the dot equivalent to roughly 80 hours of direct observation. The universe gave the team more than double the data they paid for free, because the geometry happened to align. The result was the deepest, most detailed spectrum ever obtained of a little red dot. More than 40 individual spectral lines were identified in the data. Each line is a fingerprint from a specific element or physical process. Hydrogen lines, oxygen lines, helium lines, 16 iron lines, all bunched together in a dense cluster that the team nicknamed the Iron Forest. Lines showing absorption, emission, fluorescence. Vasily Kokorev, the lead author of the paper describing GLIMPSE 17775, described the experience of seeing that spectrum for the first time. The pieces of a puzzle scattered on the floor, then gradually assembled. Some pieces looked like nothing. Then 2 came together, then more. Then suddenly, there was a picture. That picture was unambiguous. Every single one of those 40-plus spectral lines was consistent with one explanation: a rapidly accreting black hole buried inside a dense cocoon of hot, partially ionized gas. The lines that should be narrow were broadened by electron scattering in exactly the way the cocoon model predicted. The ratios between certain lines required a high-energy source, specifically the ultraviolet and X-ray radiation from an accretion disk, to produce the observed intensities. The helium absorption and fluorescence both independently pointed to an extremely dense medium surrounding a powerful central source. I think part of the scientific community is converging on a singular picture, Kokorev said, after the paper was published in the Astrophysical Journal in June 2026. One puzzle piece had been strange: the classic spectral feature of little red dots, a dip in the spectrum called the Balmer break, was weaker in Glimpsey 17775 than in other dots. But the combined Webb and Hubble data explained it, and that explanation opened a new layer of the story entirely. Einstein published his general theory of relativity in 1915. One of its predictions: mass bends space, and light follows the curves of space. Near a massive object, light does not travel in a straight line. It curves around the mass, following the warped geometry of space, like a ball rolling in a curved bowl. This was confirmed in 1919 when astronomers observed stars near the Sun during a total solar eclipse. The stars appeared shifted from their expected positions because the Sun's gravity had bent the light coming from them. The newspapers called it a revolution in science. Einstein became the most famous scientist in the world. The effect scales with mass. A star bends light a little, a galaxy bends light more. A cluster of hundreds of galaxies, containing not just their visible stars but enormous halos of dark matter, adding even more gravitational pull, bends light dramatically. Objects behind the cluster are magnified, distorted, sometimes split into multiple images, sometimes stretched into glowing arcs that curve around the cluster's edge. Abell S 1063 is one of the most studied such clusters precisely because it is such a powerful natural lens. Webb has observed it multiple times for multiple science goals, using the cluster's lensing power to study objects far too faint to see directly. The cluster has revealed background galaxies, amplified faint signals, and now, accidentally, provided the clearest portrait yet of a little red dot. Glimpsey 17775 sits at a redshift of 3.5, meaning the universe had been expanding for about 1.5 billion years when this dot's light was emitted. The cluster Abell S 1063 sits much closer, at a redshift of around 0.4. The dot is behind the cluster. The cluster's gravity bends the dot's light toward us and amplifies it, like a glass magnifying lens concentrating sunlight onto a point. The amplification factor was roughly 3. That means the light arriving at Webb from Glimpsey 17775 was approximately 3 times brighter than it would have been without the lensing. Since the team observed for 30 hours, the effective depth of the observation was equivalent to 90 hours of direct telescope time. For context, Webb's most ambitious surveys allocate only a few hundred hours total. A single object getting 90 hours of effective depth is extraordinary. This accident of geometry produced a spectrum with enough signal to detect more than 40 spectral lines, where a typical little red dot spectrum might show 10 or 15. Each additional line is an independent data point. Each independent data point is another test of the model. 40 tests, all pointing the same direction, is not a coincidence. It is a result. The gravitational lensing also distorted the apparent shape of Glimpse 17775 slightly, which is why the team needed the Hubble data to reconstruct the full picture. Hubble's images, taken at shorter wavelengths over many years as part of the Frontier Fields program and its successor survey, provided the shape information that Webb's spectrum couldn't supply alone. Together, the two telescopes, one old, one new, one seeing visible light, one seeing infrared, assembled something neither could have built alone. This kind of multi-telescope science is increasingly how the biggest discoveries happen. Not one instrument with all the answers, but several instruments, each revealing a different layer, combined into a picture that none of them could produce individually. Glimpsey 17775 was the deepest look yet at a little red dot, but what it revealed went far beyond one object, because the spectral lines in its data carried physical measurements that confirmed something the entire field had been building toward for 3 years. The measurements were so specific, so detailed, and so mutually consistent that the cocoon model was no longer a leading hypothesis. It was the answer: 16 iron lines, all in a single spectrum, all clustered together in a tight band of wavelengths that the team at the University of Texas named the Iron Forest. Iron is not a simple element to work with spectroscopically. It has 26 electrons in a neutral atom, which means there are 26 electrons that can be knocked off in different combinations at different energy levels, each producing a different spectral fingerprint. Highly ionized iron, meaning iron that has lost many of its electrons, produces lines at very specific high-energy wavelengths. The configuration of those lines, which ones appear, how strong they are relative to each other, and where exactly they fall in the spectrum, all depend sensitively on the physical conditions of the environment producing them. To produce the 16 iron lines observed in Glimpsey 17775, the gas environment needed to be simultaneously hot, dense, and flooded with high-energy radiation. The ratios between the lines required a radiation field consistent with an accretion disk around a supermassive black hole. A galaxy full of stars produces a completely different radiation field and cannot produce the iron line patterns seen in the data. This is what makes the iron forest so significant. Each of the 16 lines is an independent measurement. They were produced at different wavelengths by different physical processes involving different ionization states of iron. They are connected only by the fact that they all require the same environment to exist simultaneously. Getting 16 of them to appear at exactly the right wavelengths and intensities is like getting 16 different witnesses to independently describe the same event in identical detail. The iron forest was not the only compelling feature in the Glimpsey 17775 spectrum. The oxygen lines told a similar story. Oxygen in certain high ionization states, meaning oxygen atoms that have lost most of their electrons, requires extremely energetic radiation to produce. The kind of energetic radiation that comes from an accretion disk at millions of degrees, not from the cooler, less energetic radiation of ordinary stars. The helium features added another layer. Helium was seen both in emission and in absorption in the same spectrum at specific wavelengths that pointed to a very dense, partially opaque medium surrounding a powerful source. Helium, in this configuration, is seen in known active galactic nuclei, feeding black holes when the surrounding gas is dense enough to trap and reprocess radiation. And underneath all of these individual features, the overall shape of the spectrum, the smooth background on which all the lines sat, showed the electron scattering signature, a specific broadening and rounding of the continuum emission that only occurs when light is passing through enormous concentrations of free electrons before escaping. The Copenhagen team's work and the University of Texas team's work had converged on exactly the same answer from two different angles. Hundreds of dots giving a statistical portrait, one dot giving an extraordinarily detailed single portrait. Both portraits showed the same face, but the story was not yet complete. One feature in Glimpsey 17775 spectrum was weaker than expected. The Balmer break, a dip in the light at a specific wavelength that is a classic signature of little red dots, was missing much of its expected strength. That absence had a separate explanation, and it revealed something about the dots that no one had yet included in the picture. The word spectrum gets used constantly in astronomy, but what it actually is, and what it actually shows, is worth making concrete before going further, because the entire case for the cocoon model rests on reading one. Take sunlight and pass it through a glass prism. It fans out into a rainbow. That rainbow is a spectrum, the light spread out by wavelength so that you can see each wavelength separately instead of all blended together into white. Every photon of sunlight is still there. The prism just sorts them by color. Now imagine a more precise instrument, one that spreads light not just into a rainbow, but into a very fine band where each wavelength is separated from its neighbors by a tiny fraction. Where the rainbow is a blur, this instrument produces a sharp, detailed strip. You would see not just a smooth transition from red to blue, but something more complex, a mostly smooth continuum with specific bright spikes and dark gaps interrupting it. Those spikes and gaps are the spectral lines. Bright spikes are called emission lines. Gas somewhere has absorbed energy and is re-emitting it at a specific wavelength. Dark gaps are called absorption lines. Gas is absorbing incoming light at that wavelength before it reaches you. Each element has its own pattern of lines, always at the same wavelengths, regardless of where in the universe it is. Hydrogen's lines are hydrogen's lines, whether the gas is in your own galaxy or 13 billion light-years away. The instrument astronomers use to produce spectra is called a spectrograph. Webb carries one called NIRSpec, the near-infrared spectrograph, which can capture the spectra of multiple objects simultaneously by using tiny mirrors smaller than a fingernail to direct light from specific points in an image into separate channels. The result is a data product that looks like a strip of colored information with bright and dark lines encoded in it, which scientists then analyze computationally. Reading a spectrum is a precise, methodical process. Each line is measured for its position, its width, and its strength. Position tells you what element is producing it and how fast the gas is moving relative to you. Width tells you the temperature and turbulence of the gas and whether electron scattering is at work. Strength, particularly the ratio of one line's strength to another's, tells you the density, temperature, and radiation environment. For GLIMPSE 17775, the NIRS spec instrument captured more than 40 of these lines. Each one was measured, identified, and compared against models of different physical environments. A galaxy full of stars produces one set of predictions. A black hole with an accretion disk produces a different set. A black hole inside a dense ionized cocoon produces a third, very specific set. The GLIMPSE 17775 spectrum matched the third set. Every single line, every ratio, every shape, every absorption and emission feature. The match was not approximate. It was precise enough that the team could infer the density of the cocoon's electrons, the size of the region producing the lines, and the approximate mass of the central black hole, all from the same strip of data. This is what spectrum reading can do when the data is deep enough. It can tell you the physics of an object from over 13 billion light-years away, more precisely than you could measure many things in your own city. GLIMPSE 17775 gave the clearest spectrum of any little red dot ever obtained, and that spectrum told a complete story, with one small loose end. That loose end required looking at an entirely different feature of the object, one that Webb's spectrum alone couldn't supply. Every little red dot has a signature dip in its spectrum, at a specific wavelength corresponding to the energy needed to knock an electron completely off a hydrogen atom. The light drops sharply. Below that energy, the spectrum is bright. Above it, the light fades. This feature is called the Balmer break, and it is one of the defining characteristics that astronomers use to identify these objects. In GLIMPSE 17775, the Balmer break was unusually weak, barely there. For a spectrum otherwise packed with signatures matching the black hole cocoon model, this absence was a loose thread that competing theories could pull on. Other little red dots showed strong Balmer breaks. The standard explanation for those breaks, in the original galaxy hypothesis, was that they came from an aged stellar population. When a burst of star formation ends and the hot blue stars die first, what remains is a population of cooler, redder stars. The light from those older stars naturally drops off at the Balmer break wavelength. This is a standard feature of galaxies that had their stars form all at once in the past. If the Balmer break came from stars, GLIMPSE 17775 should have shown it too. Its absence suggested either a different history or an additional light source filling in the gap. The team went back to the Hubble archive. The Frontier Fields program and its successor survey had imaged the Abell S 1063 region with Hubble at multiple wavelengths over many years. Those images showed something Webb's spectroscopy had not resolved. GLIMPSE 17775 was surrounded by a giant host galaxy. A host galaxy is the larger system within which the active black hole sits. In nearby active black holes, the host galaxy is always visible surrounding the bright central nucleus. In the little red dots, the host galaxy had been assumed to be small, faint, and essentially invisible, overwhelmed by the black hole's light. Glimpse 17775's host was neither small nor faint. It was large, containing a significant number of stars, and it was contributing blue light to the overall spectrum. That blue light from the stars in the host galaxy was partially filling in the Balmer break, making it appear weaker than it actually was in the black hole system alone. Once the contribution from the host galaxy's stars was modeled and subtracted, the remaining spectrum matched the cocoon model precisely. The puzzle piece fit. The weak Balmer break was explained, and in being explained, it revealed something new. The host galaxies of little red dots could be significantly larger than assumed. Previous work had largely treated the host as negligible. Glimpse 17775 showed that at least some dots sit inside substantial galaxies. Galaxies with their own star populations, their own history, their own evolution running in parallel with the black hole's growth. This is also what Kokorev meant when he said, "Everything fits, nothing is broken." The Balmer break that had seemed like a problem turned into a measurement. The weakness of the dip became a ruler for the size of the host galaxy. What looked like an inconsistency was actually additional information. With the spectrum complete and the host galaxy accounted for, the picture of Glimpse 17775 snapped into focus. A supermassive black hole inside a dense ionized cocoon, wrapped in a large and actively star-forming host galaxy, all seen through the natural magnifying effect of a foreground galaxy cluster, all recorded in the deepest spectrum ever taken of this class of object. The case was closed, but the implications of what had just been confirmed were only beginning to be absorbed. The discovery of Glimpse 17775's large host galaxy wasn't just a footnote to the spectrum analysis. It changed a key assumption that had been baked into the little red dot debate from the beginning. Since 2022, when the original 13 red blobs were found and flagged for impossible masses, the conversation had focused on two alternatives. Either these were massive galaxies, or they were active black holes in small galaxies. The first option broke the cosmological model. The second resolved it. Most researchers moved toward the second. But Glimpse 17775 suggests a middle path. The galaxy is not the dominant source of light, so the mass estimates from brightness don't apply to it the way they would to a normal galaxy. But the galaxy is genuinely large, with real stars, real structure, real mass in its own right. It is not negligible. This means the standard assumption that little red dots are just compact black holes in tiny faint host systems is at minimum incomplete. Some dots sit inside substantial galaxies. The black hole and the galaxy are co-evolving, growing together. The black hole eats and generates energy. That energy outflows into the galaxy. The galaxy provides the large-scale gas reservoir from which the cocoon is partially drawn. The relationship between a supermassive black hole and its host galaxy is one of the oldest unsolved puzzles in modern astrophysics. Scientists have found a remarkably tight correlation in today's universe. The mass of a galaxy's central black hole is always a specific fraction of the galaxy's total stellar mass, not a rough ratio. A tight, consistent one. Galaxies with more stars have proportionally more massive black holes. This correlation holds across a huge range of galaxy sizes and black hole masses. It strongly implies that galaxies and their black holes grow together, regulated by the same processes, not independently. But the mechanism of that regulation, exactly how the black hole and galaxy communicate and influence each other, is still debated. The little red dots may be showing scientists that coevolution in action, in its earliest, most violent form. The black hole is growing fast in its cocoon. The host galaxy is building stars around it. Energy from the black hole is shaping the galaxy. Mass from the galaxy's gas is feeding the black hole. Two processes, intertwined. If future Webb observations confirm that many little red dots have significant host galaxies, it will shift the focus of the field. The story will stop being about the black hole alone and start being about the black hole and its environment growing together, a partnership that began in the universe's first few 100 million years and continued for billions more. The fact that Glimpsey 17775's host galaxy was only visible because of Hubble, not Webb, reinforces another lesson. The most complete pictures always come from using multiple tools, different wavelengths, different resolutions, different detection methods. Science at this scale is rarely solved by a single instrument, but there is still the fundamental question that all of this has been building toward. The dots are identified, the mechanism is understood, the growth spurt is confirmed, but where did these black holes first come from? How does a universe that started with only hydrogen and helium gas produce, within its first few 100 million years, black holes heavy enough to anchor a galaxy? The answer involves one of the most dramatic events imaginable: the direct collapse of an entire gas cloud, millions of times the mass of the Sun, falling inward all at once with nothing to stop it. Standard black holes form at the end of a star's life. A massive star burns through its nuclear fuel over millions of years. When the fuel runs out, the outward pressure that kept the star inflated disappears. Gravity wins instantly and catastrophically. The outer layers explode outward in a supernova. The inner core collapses inward. If the core is massive enough, the collapse does not stop. No force in the universe can resist the infall once enough mass is concentrated in a small enough volume. A black hole forms. These stellar mass black holes, weighing 10 to 100 times the mass of the Sun, are the seeds of the universe's black hole population. In principle, they can grow into supermassive black holes by merging with each other and by eating surrounding gas over billions of years. In practice, that growth is too slow. The mathematics of accretion at the Eddington limit, starting from a stellar mass black hole and trying to reach 1 billion solar masses in less than a billion years, does not work without the black hole starting from a much heavier seed than a collapsed star provides. This is where direct collapse enters. The hypothesis is that in the very early universe, before stars had seeded the gas with heavy elements, massive clouds of pristine hydrogen and helium could bypass the star formation stage entirely. Under the right conditions, a cloud of gas containing perhaps 100,000 solar masses of material could collapse directly into a single object without fragmenting into smaller clumps. Normally, gas clouds cool and fragment as they collapse, breaking apart into many smaller pieces, each of which becomes a star. But in an environment with very little ability to cool efficiently, which the early universe provided, given its lack of heavy elements, the cloud could collapse as a whole unit. The result would be a black hole with a starting mass of perhaps 10,000 to 100,000 solar masses. That is 100 to 1,000 times heavier than a stellar mass black hole. It is a head start that makes the race to supermassive scale vastly more manageable within the available time. These hypothetical objects are called direct collapse black holes. They were proposed decades before Webb launched as a theoretical solution to the problem of early supermassive black holes. Webb is now providing the first observational evidence that they may actually exist. The little red dots appear at exactly the time when direct collapse black holes are predicted to be forming and entering their first growth spurt. Their masses, once corrected for the cocoon contribution, match the range expected for direct collapse seeds that have been accreting rapidly for a few 100 million years. One research team used detailed computer simulations to model a direct collapse black hole and its surrounding galaxy evolving together through the first several 100 million years. The simulation produced an object at the end of its rapid growth phase that looked, in its spectrum and brightness and color, strikingly similar to the little red dots Webb found. The match was not perfect. Simulations never are. But the core prediction held. direct collapse followed by a furious cocoon-fed growth spurt, then a transition to quieter growth, is a plausible path from the early universe's raw gas to the supermassive black holes anchoring today's galaxies. The question of what triggered direct collapse, what conditions allowed some gas clouds to skip star formation entirely, has more than one potential answer. One of them involves a source of energy that remains completely invisible to every telescope ever built. Dark matter makes up about 85% of all matter in the universe. Every galaxy sits inside a halo of it, far larger than the visible galaxy itself. The dark matter halo is the gravitational scaffolding on which the visible gas and stars are built. Without dark matter, galaxies as we know them would not exist. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter through any force except gravity. Scientists have been trying to detect it directly since the 1970s, using sensitive underground detectors, particle accelerators, and observations of gravitational effect. They have confirmed it exists by how it shapes the universe around it. They have not yet identified what particle or particles it is made of. But a new and fascinating theory proposes that dark matter does something it was never expected to do. It slowly decays. If dark matter particles decay, they release a tiny amount of energy not into visible light, but into the surrounding environment. A team of researchers from the University of California at Riverside calculated what would happen if dark matter in the halos of early galaxies was releasing small amounts of energy into the surrounding hydrogen gas. The amount of energy needed is extraordinarily small. Each decaying dark matter particle would need to release only a billion trillionth of the energy stored in a single AA battery. Individually, each decay event is nearly nothing. But in the early universe, with dark matter halos containing enormous numbers of particles, the collective effect adds up. The team found that enough energy released through dark matter decay could heat the gas in certain halos in a very specific way, hot enough to prevent the gas from fragmenting into many small clouds that would form stars, but not so hot that the gas disperses entirely. The gas would stay together in a single, massive cloud, unable to form stars, slowly cooling just enough to eventually collapse in one piece. That is exactly the condition required for direct collapse. The dark matter, by leaking a tiny fraction of its energy into the gas, would be suppressing star formation and enabling the gas cloud to fall inward as a whole rather than breaking apart. If this mechanism is real, dark matter is not just the passive structural skeleton of the universe. It is an active participant in the formation of the first black holes, the invisible component of the cosmos, the 85% that no telescope has ever seen, may have quietly engineered the seeds of every supermassive black hole that exists today. This idea remains a strong scientific possibility rather than confirmed fact. It is supported by the mathematical consistency of the calculations, but has not yet been tested against specific objects. Webb's continued observations of the early universe will provide more data points, and future, more sensitive observations may eventually find the signatures of direct collapse black holes in the process of forming, not just after their initial growth phase has begun. What is already clear is this: the little red dots are not just about black holes. They are about the connection between the invisible dark matter universe and the visible one, between the 85% we cannot see and the 15% we can. Every galaxy, every star, every atom of carbon in every living thing on Earth exists within a dark matter halo that may have been actively shaping cosmic history from the very beginning. That is a profoundly different picture of the universe than the one scientists held just a few years ago. The Milky Way is not a passive backdrop to human history. It is a living structure, and at its center, 4 million miles below the southern sky, as seen from Earth, actually 4 million solar masses, at the end of a 26,000 light-year journey, inward sits a supermassive black hole named Sagittarius A star. It is quiet now, It occasionally flares when a passing star gets too close or a small cloud of gas drifts within reach. But for most of its history, and certainly for the last few billion years, it has been dormant, a sleeping giant. The little red dots tell the story of when giants like Sagittarius A star were awake. The black holes powering the little red dots weigh up to about 10 million solar masses. Sagittarius A star, at 4 million solar masses, falls squarely within that range. The Milky Way's black hole is almost certainly a grown and quieted version of something that, 13 billion years ago, went through exactly the kind of violent, cocoon-fed growth spurt that Webb is now watching in other galaxies. The timing fits, the mass fits. The only thing that differs is the current state. In the early universe, the black hole was still surrounded by its dense gas cocoon, eating furiously. Today, the cocoon is long gone. The black hole's food supply has been exhausted or dispersed. What was once a little red dot has become a quiet, dark point at the center of a mature spiral galaxy. This realization carries a specific and remarkable weight. The light, still arriving at Earth from the little red dots, left those objects when the Milky Way itself was just beginning to assemble. The gas clouds that would eventually form the Sun, Earth, and every living thing on this planet were still raw hydrogen and helium drifting through space. Somewhere in the universe, billions of years before this solar system existed, a tiny red dot was glowing at the center of what would become a galaxy like ours. Webb is watching our own origin story, told by someone else's past. The connection goes deeper still. Supermassive black holes don't just sit at the centers of galaxies, they shape them. The outflows and radiation from a feeding black hole heat the surrounding gas, prevent new star formation, control how much mass a galaxy accumulates, and regulate the galaxy's size over billions of years. The Milky Way's current structure, the number of stars it contains, the rate at which it still forms new stars, all of it was partially determined by the activity of Sagittarius A star in its early violent phase. Every star in the Milky Way exists partly because of how the central black hole managed its growth and regulated the gas supply around it. Including the Sunday, including Earth, including every atom in your body. The little red dots are not just ancient curiosities, they are a direct part of the chain of events that produced us. Before the little red dots, before the first black holes, before any structure in the universe existed at all, there was a moment when the first star ignited. That moment was profoundly different from every star formation event that has happened since. The gas of the early universe was almost entirely hydrogen and helium, nothing else. No carbon, no oxygen, no silicon, no iron. The periodic table beyond helium simply did not exist yet. It had to be built, atom by atom, inside the cores of the first stars. Those first stars, which astronomers call population 3 stars, are theoretical. Nobody has ever directly observed one. They existed in the universe's first few 100 million years, and they are so far away and their light so ancient and stretched that even Webb has not definitively confirmed a single example. But the mathematical case for their existence is strong, and Webb is actively searching for their signatures. Population 3 stars are predicted to have been extremely massive. The conditions of the early universe, the absence of heavy elements that help gas cool and fragment, favored the formation of enormous stars rather than the smaller ones that dominate today. Some models suggest the very first stars could have been 10,000 times the mass of the Sun, objects so extreme that nothing like them exists anywhere in the modern universe. Those massive stars burned through their hydrogen fuel at an extraordinary rate. A star 10,000 times more massive than the Sun might live for only 100,000 years, compared to the 10 billion years a Sun-like star enjoys. When they ran out of fuel, some of them collapsed directly into black holes without exploding as supernovae. The mass was too great, the collapse too fast, for an explosion to overcome the infall. These deaths created black holes of several thousand to tens of thousands of solar masses, still not the hundreds of thousands needed for direct collapse black holes, but far heavier than the stellar mass seeds of today's universe. A population 3-star remnant black hole, if it found itself inside a dense hydrogen gas cloud and began eating rapidly, could potentially grow to the masses seen in the little red dots within a few 100 million years. The little red dots may therefore sit at the end of a 3-stage process. Stage 1. Population 3 stars form and die, creating the first black hole seeds. Stage 2. Those seeds fall into dense gas clouds and trigger or participate in direct collapse events, building heavier starting points. Stage 3. The heavy seeds begin the furious cocoon-fed growth spurt that Webb is watching in the dots. This chain connects the very first stars to the supermassive black holes that now anchor every large galaxy in the observable universe. Every step in the chain produced something that the next step required. The first stars seeded the first black holes. The first black holes grew into the monsters that regulated the first galaxies. The first galaxies evolved into the ones we live in today. Webb may, in the next few years, confirm the existence of population 3 stars by finding galaxies at redshifts above 15, just 200 million years or less after the Big Bang. If those early signatures match the predictions, the chain will be complete from beginning to end, and the little red dots will sit exactly in the middle of that chain, where they belong. In early 2023, headlines announced that Webb had found galaxies that broke cosmology. The phrase "spread fast." It implied that the standard model of how the universe works was fundamentally wrong, that everything scientists thought they understood about the Big Bang and the formation of cosmic structure was suspect. That framing was always more dramatic than the science warranted, and the resolution of the little red dot mystery makes that clear. The standard model of cosmology, called lambda CDM, describes the universe's history from the first fractions of a second after the Big Bang through the formation of galaxies and large-scale structure today. It uses dark matter, dark energy, normal matter, and the known laws of physics to predict what the universe should look like at different points in time. It has been tested against decades of observational data and has proven remarkably durable. When the first Webb images showed apparently massive objects in the very early universe, some researchers interpreted it as evidence that lambda CDM was wrong. If galaxies that large could exist that early, the model's predictions about the rate of galaxy formation were off by a factor large enough to demand revision at the fundamental level. But the cocoon model changes that story entirely. The objects were not massive galaxies. They were feeding black holes. Their brightness came from accretion, not from hundreds of billions of stars. The mass estimates based on brightness were wrong because they used the wrong assumption about the source of the light. Correct the assumption. Reduce the mass by a factor of 100, and the objects are no longer impossible. The standard model does not need to be broken to accommodate black holes of 10 million solar masses existing 600 million years after the Big Bang. Direct collapse black hole formation, possibly accelerated by dark matter energy injection, can produce seeds heavy enough to reach that mass within the available time, without requiring any new physics. Kokorev said it directly: everything fits, nothing is broken. This outcome is worth pausing on because it reveals something important about how science handles anomalies. The first instinct when observations don't match predictions is to question the model. Sometimes that instinct leads to genuine revisions. The discovery that the universe's expansion is accelerating due to dark energy was a genuine case where the model had to change. But sometimes, the anomaly is in the interpretation of the data, not in the underlying physics. The little red dots were observed correctly. Their brightness was measured correctly. The problem was the step between observation and conclusion, the assumption that the brightness came from stars rather than from a black hole. Change that one assumption and the anomaly dissolves. This does not mean the standard model is perfect. Webb continues to find objects at extreme distances and with unusual properties that will require careful interpretation. Some of those objects may ultimately require genuine revisions to the model. But the little red dots are not among them. They fit beautifully, completely, consistently. The universe was not broken. Scientists were reading the same page twice, in two different languages, and getting confused between them. Black holes are often described as purely destructive, objects that take in matter and give nothing back. The reality of how they interact with their host galaxies is far more complex and far more essential to the existence of the universe as it is today. When a supermassive black hole feeds, it does not consume everything around it. It ejects vast quantities of material at high speed. The jets launched from the poles of the black hole, the outflows driven by radiation pressure from the accretion disk, and the wind blown off the outer edges of the disk all carry energy into the surrounding galaxy. This energy heats the gas. Heated gas does not collapse into new stars easily. Hot gas expands, rises, and disperses rather than cooling and fragmenting into star-forming clumps. This means a feeding black hole actively suppresses star formation in its host galaxy. The more vigorously it feeds, the more energy it dumps into the surrounding gas, the harder it becomes for new stars to form. Scientists call this feedback. The black hole feeds back into its environment in a way that regulates its own growth and the growth of the galaxy simultaneously. Without feedback, galaxies would accumulate stars indefinitely. Gas would keep cooling and collapsing, generation after generation, building up stellar masses far beyond what we observe. The most massive galaxies in the universe today are already somewhat too large to be easily explained by models without feedback. With unregulated star formation, they would be even larger. The little red dots were providing feedback at the most critical moment, the universe's first billion years, when the first galaxies were deciding how large they would become. The intense radiation from the dots' black holes heated gas in and around the host galaxies, setting limits on how fast stars could form and how much mass could accumulate. The galaxy that emerged from that regulated environment was shaped, in part, by the black hole at its center. This is why the tight correlation between black hole mass and galaxy mass exists in today's universe. The relationship was built into the system from the beginning, set during the violent growth spurt era that the little red dots represent. Black holes and galaxies did not grow independently and happen to match. They grew together, regulated by the physics of accretion feedback from the first moments when both existed. Webb has now watched that regulation happening in hundreds of objects in the universe's earliest accessible era. The dots are not just scientifically interesting, they are causally responsible for the structures that exist everywhere around us today. Every galaxy visible in the night sky, every elliptical, every spiral, every irregular dwarf galaxy, all of them contain the legacy of a growth spurt like the ones the little red dots represent. All of them were shaped by a period when their central black hole was feeding furiously inside a dense gas cocoon, regulating the gas supply, setting the terms of the galaxy's development for billions of years to come. The violence of the early universe was architectural, and the blueprints it drew are still standing today. X-ray astronomy began in 1962 when a team launched a small detector above Earth's atmosphere on a rocket and detected X-rays coming from a source in the constellation Scorpius. Before that night, nobody knew the universe produced X-rays in detectable quantities. Within a decade, X-ray observatories had revealed neutron stars, black hole binaries, galaxy clusters filled with superheated gas, and the first confirmed active supermassive black holes. The Chandra X-ray Observatory, launched in 1999, pushed that science to its current limits. Chandra can resolve X-ray sources to within fractions of an arc-second, sharp enough to separate the X-ray emission from the center of a galaxy from the emission of the galaxy's surrounding gas. It has been the premier X-ray telescope for more than 2 decades. When the little red dots were identified as candidate black holes, Chandra was pointed at them. The initial results were puzzling. Very little X-ray emission. Active black holes should shine brightly in X-rays. These didn't. That silence deepened the mystery and fueled the debate between the galaxy mass and black hole hypotheses. The cocoon model predicted a specific resolution to the X-ray silence. The dense, ionized cocoon should absorb most of the X-rays produced by the inner accretion disk, converting them to infrared. But most is not all. Some X-rays, particularly harder, more energetic X-rays with shorter wavelengths, should be able to scatter through the cocoon at angles that allow partial escape. The expected X-ray signal would be faint, much fainter than typical active black holes, but detectable with enough exposure time. Teams combining Chandra and Webb observations of the same little red dot fields found exactly this. Stacking many hours of Chandra exposure on regions where Webb had identified little red dots, they detected faint X-ray signals at positions consistent with the dots. The signals were weak, heavily suppressed, exactly as the cocoon model predicted. The column density of gas required to suppress the X-rays by the observed factor matched the column densities inferred from the infrared spectra. This kind of cross-telescope confirmation is particularly powerful in science. Webb and Chandra observe in completely different parts of the electromagnetic spectrum, using completely different instruments, with completely different sources of potential error. When both independently produce results consistent with the same physical model, the model is substantially strengthened. The confirmation also demonstrated that the little red dots are not X-ray quiet because they lack black holes. They are X-ray quiet because their black holes are wrapped in gas thick enough to absorb almost all the X-rays produced. Strip away the cocoon and the same objects would look like ordinary quasars, blazing in X-rays. The cocoon is what makes them look different. The cocoon is what makes them a distinct phase in cosmic evolution rather than just another variety of known active black hole. Adding Chandra data to the picture closed one more gap in the evidence. Between the infrared spectra from Webb, the iron forest and broad emission lines and electron scattering signatures, and the faint, suppressed X-ray signal from Chandra, every observational feature of the little red dots had found its explanation in the cocoon model. The investigation was complete, but the discoveries it enabled were only just beginning to be understood in their full scope. The answer to what the little red dots are has arrived. What that answer means is still being worked out. Researchers are clear-eyed about what remains unresolved. Kokorev, after publishing the Glimpsey 17775 paper, said he expects the final picture to take another year or two to fully solidify. The community is converging, but convergence is not the same as certainty. One open question concerns the power source inside the cocoon. The cocoon model attributes the energy to a rapidly accreting black hole that is the leading explanation, strongly supported by the spectral evidence. But some researchers have proposed alternative central engines. One suggestion is supermassive stars, single objects 1,000,000 times more massive than the Sun, so enormous that their outer envelopes become diffuse and cool, while their dense cores produce energy through nuclear burning at extreme rates. These hypothetical objects, called supermassive stars or quasi-stars, would produce a spectrum with some similarities to the cocoon model. The distinction matters because supermassive stars, if they exist, would eventually collapse directly into black holes, providing another pathway for early black hole seed formation. They would also produce slightly different spectral signatures than an accretion disk. The current data supports the black hole interpretation more strongly, but confirming it definitively requires detecting signatures that are unique to one model and absent in the other. A second open question concerns the host galaxies. Glimpsey 17775 has a large host galaxy. How typical is that? Are most little red dots embedded in similarly substantial systems? Or is Glimpsey 17775 unusual? Answering this requires similarly deep, multi-telescope observations of many more dots, a campaign that will take years of Webb time to complete. A third question concerns what happens to the cocoon as it is consumed. The model predicts that the black hole eats through its fuel supply and the system transitions to a quieter phase. But the details of that transition, how fast it happens, what triggers the final collapse of the cocoon, what the system looks like in the weeks or months before the dot disappears, are not yet observed. Catching a dot in the act of fading would be an extraordinary scientific event. Nobody has done it yet. A fourth question reaches back even further. What are the very first black holes? If direct collapse black holes are the seeds, what triggered those collapses specifically? The dark matter decay hypothesis is compelling but unconfirmed. Other mechanisms have been proposed. Webb is currently pushing observations toward redshifts above 12 and 13, looking for the signatures of the very first structures, trying to catch the universe before the dots appear. If those observations find the precursors to the dots, the dense gas clouds poised to collapse, or the very first black hole seeds, just beginning to eat the chain from the Big Bang to today's galaxies, will be complete. The universe is not finished being strange. It is just beginning to be understood. The little red dots are 13 billion years old. They are abstract, they are invisible to the naked eye, and unreachable by any human technology. They exist at a distance so extreme that the number of miles is meaningless without comparison, and yet they are directly responsible for the fact that you exist. Here is the chain of connection. Every atom heavier than helium in the known universe was forged inside a star or produced during a violent stellar event. The carbon atoms in your DNA were built in the nuclear cores of massive stars that died billions of years ago. The oxygen atoms in your lungs were assembled the same way. The iron in your blood formed in the final moments of massive stars before they exploded as supernovae. You are, in a literal and measurable sense, made of ancient stellar material. Those massive stars could only exist inside galaxies. Galaxies could only develop their current structures through the regulated growth made possible by supermassive black holes providing feedback. And those supermassive black holes reach their current masses by passing through the violent, cocoon-fed growth spurt that the little red dots represent. Remove the little red dots, or interrupt that growth spurt, and the galaxies that formed afterward would be different sizes, different structures, different star formation histories, different distributions of the heavy elements that life requires. The precise chemical environment that produced Earth, including the abundance of carbon, the ratio of oxygen to silicon, the concentration of iron in the planet's core, was determined in part by the history of the Milky Way's star formation. And the Milky Way's star formation was regulated by its central black hole during its early cocoon-fed phase. Oxygen, the element you are breathing, was produced by massive stars inside galaxies shaped by black hole feedback. The little red dots were part of that feedback. They were part of the process that determined how much oxygen exists, how spread out it is, and where it ended up. This is not poetry. It is traceable physical causality. The discovery also connects to the search for life beyond Earth. Scientists looking for habitable planets in other galaxies need to understand the chemical history of those galaxies. Galaxies shaped by intense early black hole feedback, the kind the little red dots represent, may have different elemental abundances than galaxies where that phase was milder. Planets forming in those galaxies might have more or less of the elements that chemistry and biology depend on. Webb's next years of observations will refine the picture. The dots will be studied in greater numbers and at greater depth. The host galaxies will be mapped. The transition from violent to quiet will be sought. The precursors, the first stars, the first gas clouds, the very first black hole seeds will be hunted in the most ancient observable light. Somewhere in that ancient light is the starting point of a chain that runs through billions of years of stellar deaths, galactic mergers, and chemical enrichment, and arrives, eventually, here. A species looking back at the universe through a gold-mirrored telescope, trying to understand where everything came from. The little red dots were a mystery written in the universe's oldest light. Now, finally, they have been read.